Hi everyone, I'm Tushar, glad to be here. Thanks for coming. Just a quick survey. How many of you already know what SNARKs are? Perfect. I might speed through those parts because the presentation is a bit on the longer side. But if you feel like I'm ever going too fast, please raise your hand and I will slow down. Cool. So today I'll be talking about Scribe, which is a SNARK in low memory environments. We'll see what that means in a second. Let's start by revising what SNARKs are. They're an interactive protocol between a prover and a verifier, and both of them share a function f. The prover has some public input x and some private input w. The verifier only has the public input, and the prover hopes to convince the verifier that they know some w such that f of x w equals 1. And it does so by sending over a short proof that the verifier can verify in less time than it takes to compute the function itself. The prover, unfortunately, runs in more time than it takes to compute the function, but hopefully not too much more. A few properties we look for are completeness, which says whenever f of x w is indeed 1, we accept. Knowledge soundness says whenever we does accept, p must know some w such that f of x w equals 1. Succinctness says the proof is small. SNARKs are immensely useful tools in rollups, private cryptocurrencies, and a variety of other blockchain applications. A barrier to adoption, though, has been high prover overheads, especially in terms of memory. In fact, existing SNARK provers require a prohibitive amount of memory that's linear in the size of the circuit. Here's a graph of the implementation of Hyperplonk, a state-of-the-art linear prover time SNARK. You'll notice that the plot stops for circuits of size larger than 2 to the 24 gates. This is because the prover ran out of memory. So let's see what we can do about this. Or let's see what people have already tried to do about this. One line of work to solve this problem has been streaming SNARKs. In particular, Gemini proposed the read-only streaming model, where the prover has much less working memory, in fact, logarithmic in the size of the circuit, but has streaming access to the entire circuit, which is stored somewhere in external storage, let's say on a disk drive. And it can stream through this potentially multiple times and perform computations in its smaller working memory, but it does not have random access to the circuit. This is what Gemini's performance looks like. As you'll see, the working memory requirements of the prover scale only logarithmically with the size of the circuit. And the time looks nice, but what that graph doesn't show is that asymptotically, the time requirements are order of n log square n, where n is the size of the circuit. In comparison, the non-streaming baseline prover would require both linear time, but also linear working memory. We asked the question, can we do better? That is, get the best of both worlds with small working memory, logarithmic in the size of the circuit, but still linear prover time. This brings us to our first contribution. We answer in the affirmative. In the read-write streaming model, which is a relaxation of the read-only streaming model, where the prover still has small working memory and read-only access to the circuit, but also has the ability to write out to the same external storage, the disk or whatever, and it can still do so only sequentially. And so it reads from overall, it can read from the stream, it can perform computations in its small working memory, it can write out things to the write stream, it can switch freely between these two things, and at any point, it's also free to sort of go back and make multiple passes over either of these streams, and most importantly, it can swap a write stream that it's just written down into a read stream. And why is this helpful? One, this gives the SNARK prover the ability to sort of write out intermediate state onto a write stream and then go back and read from it. The only limitation here being that both the writing and the reading from this intermediate state have to be sequential and not random access. Okay, so that was the model. Does it help? Yes, it lets us construct Scribe, which is a streaming SNARK, in particular a streaming version of Hyperplonk. And this is our performance. We get the best of both worlds. It has linear prover time and small logarithmic working memory. Of course, it requires a it requires stream sizes on external storage that are linear in the size of the circuit. To do this, we adapt the popular compiler in the non-streaming setting to the streaming setting, where we take a streaming PIOP, a polynomial interactive oracle protocol for circuit satisfiability, and a streaming, for the rest of the talk, whenever I say streaming, I mean read-write streaming. So it also takes a streaming polynomial commitment scheme, and it puts them together to build a SNARK. In particular, we, like I said, turn the Hyperplonk PIOP for circuit satisfiability into something that works in the read-write streaming model. So what this PIOP requires is a streaming permutation check and a streaming zero check. To construct these things, we build a read-write streaming version of the sumcheck protocol, which sort of directly implies these two things. If you don't know what any of these things mean, I should go into detail about most of them over the rest of this talk. Yes, and as for streaming polynomial commitment schemes, we present a streaming version of the PST13 polynomial commitment scheme, which is a multi-linear version of the popular KZG PC scheme. And we also present streaming versions of several inner product argument-based polynomial commitment schemes, such as Dori, Hyrax, etc. Okay, so those were our theoretical contributions, but did it give us anything in practice? Yes. So we implemented our protocol in Rust using the ArcWorks framework and evaluated it over circuits of increasing size. And we saw that we're 4 times faster than Gemini, but unfortunately 2 times slower than Hyperplonk, which is in the non-streaming model, which is our baseline, essentially. So this is actually kind of an old graph, and with more recent implementation improvements, we're actually only 15% slower than Hyperplonk, so like 7 to 8 times faster than Gemini. And like we wanted, the working memory requirements scale only logarithmically with increasing circuit size. And we, in fact, concretely require much less memory than Gemini. So for this talk, to keep it on time, I'm only going to cover the streaming sumcheck protocol and the streaming version of the PST13 polynomial commitment scheme. But before we do that, let's look at the recipe for SNARKs for people who aren't super familiar with the PIOP plus PC scheme idea. Essentially, the SNARK prover and the SNARK verifier work as follows. The SNARK prover runs this thing called a PIOP prover. It simulates it internally. And so essentially, the PIOP prover and the PIOP verifier would interact to convince the verifier of some circuit being satisfiable or a function being evaluating to 1 on those inputs. And the PIOP prover would do this by trying to send few polynomials to the PIOP verifier. Unfortunately, these polynomials are usually very large. So the SNARK prover commits to any polynomials that the PIOP prover wants to send over and sends these short commitments to the verifier. And then the verifier replies with random challenges. And the SNARK prover does this as many times as the PIOP prover would like to. Once this is done, the PIOP verifier would like to verify these polynomials at certain evaluation points. Unfortunately, it can no longer do so itself because it only has commitments to these polynomials. So the SNARK prover sort of simulates the verifier's queries and then produces polynomial commitment opening proofs as well as the opening values at these points and sends these over to the verifier. The verifier checks that these proofs are valid and checks that some appropriate relation holds between these claimed evaluation values and comes to a decision. Since the verifier is public coin, you can use the Fiat-Shamir heuristic to turn this entire thing non-interactive. So let's go back to the talk outline. Let's start with the streaming sumcheck. The sumcheck is the foundation of all linear time SNARKs. This is thanks to a linear time, linear space construction due to Justin Taylor in 2013. But what is the sumcheck? It is, again, an interactive PIOP between a prover and a verifier, where the verifier has oracle access to some polynomial P, and the prover hopes to convince the verifier that the sum of the evaluations of this polynomial, so the polynomial that we care about in this case is multilinear, that is of degree at most 1 in each variable. And the prover hopes to convince the verifier that the sum of the evaluations of this polynomial over the Boolean hypercube are in fact equal to some claimed point sigma. And it wants to do this by having the verifier do much less work than evaluating the polynomial over the entire hypercube, which would take 2 raised to the little n work, where little n is the number of variables. So how the prover does this is it sends over some polynomials, and again, the verifier replies with random challenges, and they do this a couple of times. In fact, as many times as there are variables. And luckily for us, turns out in the sumcheck protocol, the polynomials the prover sends over here are univariate, so they're small and you don't have to commit to them. You can send them out in the open. So this leads to the natural question, the fact that this is such a foundational primitive leads to the question, can we achieve linear time in a read-only streaming setting using only logarithmic memory? People have tried, and most attempts have been unsatisfactory. In particular, CTY11 and BCHO22, which is Gemini, require only logarithmic memory, but take more than linear time, something like order of n log n time. Blendy, which is concurrent work, requires a little more than logarithmic memory, but it's still sublinear, but it runs in linear time, which is great. So in progress is we're trying to prove a lower bound for read-only streaming provers that says you can't hope to do much better. And so Blendy is optimal in the read-only setting. And this leads to the question, can we do better perhaps using read-write streams? We answer in the affirmative, and we construct a logarithmic space, linear time sumcheck in the read-write streaming model. So before we jump into that, let's do some multilinear polynomial warm-up. Consider a multilinear polynomial p of x equals ax plus b. Notice that p evaluated at 0 is equal to b, p evaluated at 1 is equal to a plus b, but equivalently, the coefficient b is equal to p evaluated at 0, and the coefficient a is equal to p evaluated at 1 minus p evaluated at 0. What this means is that a multilinear polynomial can be represented equivalently by its coefficients or by its evaluations over the Boolean hypercube. In particular, a multivariate multilinear polynomial, let's say something with 3 variables, can be represented by a table of size 8. In particular, pi in this table is the evaluation of p at I1, I2, I3, where I1, I2, I3 are the binary decomposition of I. How does the sumcheck prover work? So we're looking at the first round here. So how does F3 and then R3 look, right? So how does that first round work? The sumcheck prover would like to, well, first it has to send over that polynomial f3 of x. To do so, it computes a sum of all the elements of this table with even indices and the sum of all the elements with odd indices, and it sends these over to the verifier. This is essentially the first polynomial that it wants to send over. And then it receives the first random challenge R3 from the verifier. And then it performs this fold step where internally it needs to compute this new table of half the size that sort of folds P in half. And how it does this is by folding pairs of things together. In particular, these pairs are adjacent elements. And you don't really have to know where that exact folding equation came from. All you need to know is to turn this streaming. All you need to know is that we fold things that are side by side together, so this is very streaming friendly. In particular, this is how it's done by the prover. Say you start off with this table for P. The prover first has to compute the sums, so it starts with running even and odd sums, both instantiated to 0. And then it cycles through the read stream for the table, and anytime it reads an even indexed element, it adds it to the running even sum. Anytime it reads an odd indexed element, it adds it to the odd sum, and does this all through the table, and then sends these final sums to the verifier. And then it receives the first random challenge from the verifier, and now it's left to fold this table using this new challenge. How it does this is it reads a pair of elements, and then it computes the appropriate folding and writes it out onto a write stream for the new folded table Q, and it does this all through the table. And now it switches to reading from this table it just wrote out, and it's ready to do the next step where it needs to compute sums over this smaller table and then fold it further. Right. So the streaming sumcheck I just presented was just for multilinear polynomials, but we show in our paper that this generalizes to sums of products of multilinear polynomials. So P can be any polynomial that can be represented as the sums of products of smaller multilinear polynomials. This is important because our PIOP requires sumchecks over polynomials of exactly this form. And I believe the read-only streaming setting doesn't generalize quite as neatly. We also present a pre-processing variant where you can move all the write streams to a pre-processing step where you start with the table for P and then you pre-process it using write streams and you have this new thing that you've written out that's much longer. But then you begin, and then you turn that into a read stream, and then you begin to interact with the verifier using the challenges and stuff, and you only require read streams in the interactive part of this whole thing. And again, to go over our efficiency, the streaming sumcheck prover required linear time, logarithmic memory, but linear streams. So that was the streaming sumcheck. Now let's look at the streaming version of the PST13 protocol. Also, I think it's important to note that, like I said, the streaming sumcheck implies the things we really require, which are streaming permutation checks and streaming zero checks. And we show in our paper that we can easily build those two things using the streaming sumcheck while preserving the aforementioned asymptotic complexities. Right, so streaming polynomial commitment schemes. I won't be going over the setup for PST, one, because it doesn't have to be streaming, but also two, just to keep this talk on time. But again, we're going to treat a polynomial as a multilinear polynomial as its evaluation over the Boolean hypercube, so think of it as a table. The first thing the prover needs to do while committing to something is also interpret the commitment key as a table of group elements, and the polynomial is a table of field elements, and you essentially compute an MSM of this group vector with respect to the field vector to obtain your commitment. This can also be thought of as an inner product argument between these two things, and well, I don't show this in this talk. Perhaps if I finish early, I can come back and cycle through those slides, but this can be done with just read streams, where you can think of having a read stream for CK up here and the read stream for P, and then you the prover cycles through the entire thing, reading one from each at a time, and adds the product to a running sum. And you have the commitment at the end of the whole thing. What does PST open look like? Well, for starters, what is it trying to do? It's trying to, just to revise, PST open has some commitment to a P, and it has an evaluation point Z, and it's trying to convince the verifier that the P inside CP is in fact evaluating to Y at the point Z. How it does this is much like KZG. It computes a bunch of witness polynomials. Well, KZG is univariate, so it's a single witness polynomial. Here you have as many witness polynomials as the number of variables. But you have to compute Qi of x such that P of x minus Y is equal to the sum of Qi of x times xi minus zi. It then commits to these witness polynomials, which we've seen is easy, and sends these commitments over to the verifier. How do we compute these QIs? So let's start by decomposing P. Since P is multilinear, it is of degree at most 1 and x1, and you can split it up into these two polynomials, G and H, where H is essentially factoring out the things that have x1, all the monomials that have x1 in them. Now we can add and subtract this term, z1 times h minus z1 times h, and we see that the left side turns into some remainder polynomial r1, but the right side looks kind of exactly like we needed it to, which is x1 minus z1 times something. So h is exactly what we wanted q1 to be, and we recurse on r1 to obtain q2 all the way up to qn. But how do we do this when we're dealing with tables? So we start with a table for P, and we notice that if you plug in x1 equals 0 in this equation, you see that P of 0 and some other points is equal to G at those other points. That is, the left half of the table for P is in fact equal to the table for G. Similarly, if you plug in a 1, you see that the right half of the table for P is equal to the is equal to the table for G plus the table for H, but as we just saw, the table for G is the left half of the table for P. So the right half of P equals the left half of P plus the table for H. So we can just assign the table for G to be the left half of P, the table for h to be the right half minus the left half. And again, just to remind you, that's q1. And we compute the remainder to be g plus z1 times h. How do we do this in a streaming setting? We start with the table for p, and we have to start by pulling out the left half. So we stream through the left half, write it out to some right stream that's supposed to represent g. And then we stream through the right half and write it out to a right stream that holds the right half of p. We switch the right half to a read stream. Now we have a read stream for the right half and a read stream for the left half, which is also g. And we read through those two things to compute a difference, and we write them out. And now we have a table for h. All that we're left to do is compute a table for r. So we switch to reading from this table for h as well. And then we have the the evaluation point in memory. We have these two tables for g and h, and it's pretty straightforward. So again, you read one thing at a time, you compute the appropriate function, you write it out, and you keep going, and you're done. So putting everything together, we just saw Scribe, which was a streaming version of the hyperplonk snark, and we achieved the following asymptotic complexity: linear time, logarithmic space, but there's no free lunch, and we required access to some external storage, let's say a drive that has linear amount of memory. And this can sometimes be expensive depending on the setting you're in. Also, I think I should note here that this streaming setting is interesting because it's useful in any sort of situation where you have disparity between two kinds of memory. Something where you have a lot of memory, but it's slow, and something where you don't have too much memory, but it's very fast to compute over, like GPU memory versus CPU memory, perhaps even GPU general memory versus GPU cache memory, and then, like we just saw, CPU RAM versus disk. Yep, and again, N here is the size of the circuit, and this is what our tables look like again, and I think that's it. Thank you for listening. Our paper will be online soon.
Okay, we have, by the way, we're going to take everything 4 minutes beyond schedule because we started late. But, so we have time for questions. That's.
So like, great talk, by the way. So is there like in the scope of construction to sort of combine streaming model with the old sumcheck model, where you can do partly streaming and stop, like it's like basically doing blendy with the protocol. Do you think that like there's scope for doing it like that? Specifically in a GPU setting, because I can optimize for streams of cache, for instance, but there can be like many chunks, and you can also sort of do parallel processing when you have multiple devices, and you might want to sort of decide on the fly, you know what, you want to sort of stream this part, or you want to decide a priori that I will chunk my big instance, like you have like a machine learning model which you are representing the inference in terms of some GKR circuits, and you are actually doing GKR gates, and you may want to do them separately on different devices. I mean, it can arise in different complicated device settings. So,
yeah, so you can do that. Actually, another thing I should clarify from a theoretical point of view is this streaming we just presented is sequential because...
Right. I'm asking more like, can you take chunks instead of just sequential objects?
You can, in fact, do chunks. Actually, I'm just going to present something real quick. So for starters, remember I promised to come back to the commitment. Here's what it looks like. You have a stream for the commitment key and a stream for the polynomial, and you cycle through them, and you keep computing this running sum. But in fact, in practice, we batch these to apply fast MSMs. We read constant chunks at a time, and we use a fast MSM algorithm on those small constant chunks. You can do all of these things, and the streaming model is sequential, essentially, because In practice, if you know your access patterns, you can do things like prefetching and batching. It can be any sort of, well, again, you can sort of shuffle things around, but any sort of predetermined access pattern should be, is optimal in practice. This is just the easiest one to argue about. So yes, I think the answer is yes. As long as your access to the slow thing is predictable, you can always still perform computations in the slow one as well if you need to. That is, here you would see it as you write out a write stream, and then you perform some computation on the write stream as well, but that's like, that has different constants or it's slower or whatever, and then you can like come back and forth.
Oh, this is great because in GPU exactly you know where the data is all the time, so you can precisely predict the mapping of the data. So.
Yep.